The first question looks at the crosstabs table, our 2 by 2 contingency table. It looks at it from the perspective of, in general, how would we approach these chi-square problems? How would we approach odds ratio, relative risk, and so on and so forth? And you guys can kind of use this once you've filled this in correctly. You can kind of use this as a guideline to refresh your memory as to how to calculate these things or just to check your work and so on and so forth. Okay, so I'm gonna go over to a something I can write on, and I'm gonna pick this up. But basically, what I'm asking for here is what's the risk of illness of exposed? What are the odds of illness of exposed? Risk ratio, odds ratio, the overall prevalence of illness, the degrees of freedom for chi-square, and actually how to go ahead and calculate the critical value for chi-square or even chi-square itself. Okay, so I'm going to pull this page up, and I've repeated that table. And basically, that contingency table, if you remember, it's very similar to the table that we were working with when we were working with. Let me just check a couple of questions here. Oh, good. Okay, I'm glad some people did like having this table available. Okay, so calendar, very similar to your diagnostic testing table. We define our rows as, instead of being the result of a test, it's an exposure usually. Okay, exposure to asbestos, yes or no. Top row would be yes, bottom row would be no. Exposure to secondhand smoke, exposure to allergens, exposure, and so on and so forth. Okay, and we define our columns as being the result of that exposure. Did an illness develop? Did a condition develop? Did something improve or get worse? Yes for the first column, no for the second column. Okay, so when we want to define what our risk is, right? Our risk, okay, and first I'm going to do some addition. Okay, the number of people that were exposed in this particular group of people is A plus B. Okay, A represents the number of people that were exposed that became ill, the number of people that were exposed that didn't become ill, the number of people that were exposed that were not exposed that became ill, the number of people that were not exposed that didn't become ill. Okay, so the total number of people exposed is just A plus B. Total number of people not exposed is C plus D. Well, how many people actually became ill out of all these people? Well, A plus C is the number of people that became ill. The total number of people that didn't become ill is B plus D. And what's the total number of people in this study? Well, that's going to be A plus B plus C plus D. Okay, so now let's say that we're interested in interpreting what the risk is for exposure. So the risk for the exposed group is going to be equal to, well, A number of people got the disease out of A plus B that were actually exposed. So the risk is A over A plus B. Okay, well, what's the risk if you're not exposed? Okay, well, that's going to be C number of people became ill out of C plus D people that were not exposed. So it's C over C plus D. Okay, now our relative risk is just a ratio of those two numbers. So our relative risk is going to be equal to A over A plus B divided by C over C plus D. Okay, when we're dealing with numbers, that's actually going to be even a little bit simpler. Okay, now our odds are a bit different, aren't they? Okay, odds, instead of looking at the number of people that became ill versus the number of people that were exposed that became ill versus the total number of people that became ill, we're looking at the relationship between the number of people that became ill that were exposed and the number of people that didn't become ill if they were exposed. If these two numbers are the same, right? Well, if these two numbers, if there's 50 people that became ill and 50 people that didn't become ill, well, then it's a 1-to-1 ratio, isn't it? It's 1-to-1 or 1. Okay, so our odds are equal to A for exposed is equal to A over B. Okay, our odds for people for not exposed are going to be C over D. Okay, so if there are 10 people in this group, one of them became ill, 9 of them didn't, for a total of 10 people. Well, then the risk of being exposed, risk of illness for this group, this particular group, is going to be 1/10, right? But the odds are going to be 1/9 or 1 to 9. Okay, 1/10, 1/10, or 1/9. Okay, so we get a slightly different number, but in general, these numbers are pretty similar. Okay, so what's our odds ratio? Well, odds ratio again is a fraction, right? It's going to be A over B divided by C over D. Okay, for a number of reasons that maybe we'll discuss a little bit later on. For a number of reasons, odds ratio happens to be used very widely in epidemiology, and we'll talk about that a little bit later on. Okay, so that's what our odds are. That's what our relative risk is. This is what our odds ratio is. Relative risk or risk ratio and our odds ratio. Okay, if everybody pretty comfortable with that. Okay, so let me take a quick look at the questions. I much more frequently. I noticed that relative risk, is used very frequently in foodborne disease studies. For one thing, I don't know why in those particular kinds of studies, but odds ratios usually is the more commonly used of these two things. I don't want to get stuck right now on why you would choose one over the other, but they're very similar ways of measuring the same thing. Okay, so I'm going to go ahead. I'm going to move on to chi-square using the same box. Let me redraw it. Oops. Okay, A, B, C, D. This is exposed, not exposed. And this is illness, and this is ill, not ill. Okay, so now let's take a look at prevalence, where prevalence comes in here. So A plus B, C plus D, A plus C, B plus D, and A plus B plus C plus D is the total number of people in this study. Okay, so now let's take a look at prevalence. What's the prevalence of disease in this population of people that are presumably randomly sampled? Well, the prevalence of disease is the total number of people that got the disease over the total number of people in that sample. Okay, this is the number of people that got the disease. Some of them were exposed, some of them were not exposed. If there's a relationship between exposure and illness, we would expect this number A, or at least the proportion up here, to be higher than this number C, or the proportion down here. So the prevalence is equal to, or the probability in this population, the prevalence is equal to A plus C over A plus B plus C plus D. So we can calculate a prevalence based on what we're looking at here. So now, if we know what that prevalence is overall for this entire population, we know that when we actually did the sample, the number of people that wound up in each group is A, B, C, and D. Okay, so this is actually what happened. So what do we call this particular contingency table? What kind of values are these? These values are the observed values, right? These are the numbers that we actually got. Okay, so now, next thing I'm interested in is, well, how different is that than what I would have expected to get if there's no difference between the observed group and the expected group? And the way we're going to look at that is that we say to ourselves, well, this is the prevalence. For the moment, I'm going to call that P. Okay, so we would expect that proportion to be ill no matter what sample that we took. So if we took a sample of people that are exposed, total number of people that were exposed, A plus B, we would expect that the number of people that got sick is going to be P, whatever that prevalence is, times A plus B, right? And we would expect the difference, 1 minus P times A plus B, to be the number of people that didn't get sick within that group, A plus B. Okay, and similarly, we would expect that since C plus D is the number of people that were not exposed, right? And the prevalence overall for this population is this number that we got by looking at the total number of people. I just multiply this times that, and that's the number of people that I would expect to get the prevalence of the disease, and the number of people is C times D. I would expect P times C plus D to be the number of people that I would expect in this box, and 1 minus P times C plus D to be the number of people I would expect to see in this box. These numbers now are my expected values. If there's no difference between the rate at which exposed and unexposed people become ill, if there's no relationship between exposure and illness, in other words, our null hypothesis is that exposure and illness are independent. One does not affect the other. Okay, if that's true, then I would expect my actual values and my expected values to be the same thing, or at least very close. Okay, and that's where chi-square comes in. In chi-square, we're going to take the difference between each one of these, and the bigger the difference between each one of these, the more confident we are that there is a relationship between exposure and illness. So we're going to take the differences between each one of these, square it, divide by the expected values, and add up all those numbers, and we'll come up with a number that represents chi-square. Okay, we of course square it, because if we didn't square it when we took the differences between these, they'd cancel out. So we square it and we divide by the expected values to bring it down into the same order of magnitude as we are dealing with on these other numbers. So that value of chi-square, when we take each box cell by cell and calculate what those values of the differences are, right? When we add that up, we get some number. That number, the larger that number is, the less likely that that larger number, excuse me, let me rephrase that. The larger that number is, the less likely it is that exposure and illness are independent of one another. In other words, if this number is relatively small, then that difference between exposure and observed values is probably just due to chance. If that number is large, then that big difference is probably caused by the fact that exposure does influence whether you become ill or not. In other words, a lot of people, there's more people, or a larger proportion of people wind up here for the exposed group than wind up here for the unexposed group. Okay, so that's really what the basis of this whole chi-square thing is. Okay, now degrees of freedom. The way that we calculate degrees of freedom for a chi-square calculation or a contingency table like this is it's equal to the number of rows minus 1 times the number of columns minus 1. In this case, 2 minus 1, 2 minus 1, so the number of degrees of freedom equal to 1. So we actually can go to a chi-square distribution table, and we can look up to see what the critical value is. How big a value of chi-square that we have to get to say with 95% certainty that that number is big enough to say that there is a relationship between exposure and illness, that we can reject our null hypothesis that they are independent, or that there's no relationship between the two of them, and accept our alternative hypothesis that they're not independent, that there is a relationship between the two of them. Okay, how big does that number have to be? And how large that number has to be depends on the number of degrees of freedom. Number of degrees of freedom depends on the number of boxes. If we had a 3x2 table or a 3x3 table, in other words, high exposure, low exposure, very high exposure, and we were comparing them, and there might have been different levels of reaction or something like that. Let's say that we had a 3x3 table. Well, then potentially, because just by virtue of the fact that we have more calculations here, more cells to add up, well, a chi-square value that's larger doesn't necessarily mean that they're independent. It could just be caused by the fact that we have so many more chances for so many more ways to add to that value. So you'll find that for this, where degrees of freedom are equal to 3 minus 1, 2, 3 minus 1, 2, where 2 times 2 is 4. For 4 degrees of freedom, you'll notice that in the table, critical value for chi-square that you have to exceed in order to reject your null hypothesis that there's no relationship between exposure and illness. Well, that critical value is going to be larger than it is for 1 degree of freedom. Okay, so for 1 degree of freedom, it's somewhere around 3.8, actually 3.84 for 1 degree of freedom. So that's the number we're looking to exceed in order to say, well, there's less than 5% certainty. Well, you can do that well enough with the table, right? But if you use SPSS or some other statistical software, that'll actually calculate for you what the probability of getting that large a value is, or whatever value you happen to get. And as long as that probability is less than 0.05, you can reject your null hypothesis. Okay, so we're going to do it both ways. We're going to do it by hand, and we're going to do it by resorting to a software or SPSS. Okay, so I think we're okay on that, right? I think we covered most of it. Okay, so did I miss anything there? Overall prevalence, number of degrees of freedom, critical value, good. Okay, so now let's take a hypothetical situation. We have a church luncheon. Many attendees get ill after the church luncheon, and my experience with that is it's almost always something to do with mayonnaise. Mayonnaise, the worst thing to have at any kind of luncheon, right? So tuna salad's got a lot of mayonnaise in it, so I'm starting to think maybe that's the culprit. So we interview 100 people who ate the tuna and became ill, and we also happen to have 100 people who did not. We got lucky and got the same number of people in both groups who did not become ill. So out of 100 people who ate the tuna, 63 became ill. Out of 100 who didn't eat the tuna, 24 people reported symptoms. You know, sometimes when they have situations like this with foodborne disease, where you have kind of a symptom that's very common, such as diarrhea or upset stomach or nausea or something like that, a lot of times there's a certain psychosomatic element to this thing. So even though people maybe didn't eat the thing that caused the other people to get ill, you still may get more than a few people that report symptoms. But hopefully, if we sampled randomly and carefully, the ones that ate the material that really made them ill are going to be found at a higher proportion than the ones that just happen to have those symptoms or report those symptoms at the same time. Okay, so let's construct a contingency table for this exposure. And there's a couple of ways I could do this. One way is to use Excel, and I think I'm going to do that because it's going to save me a little bit of time. Normally, if you want, you can do it by hand. In fact, I think I have this set up here by hand. Okay, number of people that ate tuna. What did I say it was? I said it was 63 and 24. So 63 people became ill that ate the tuna, 24 people that didn't eat the tuna. So that leaves 37 people who didn't become ill out of that group of 100. And that leaves 76 people who didn't become ill in this particular group. So I'm going to open up Excel, and I'm going to do this in Excel so I can speed up my calculations a little bit. Okay, you can do this by hand or you can do it in Excel. Right, 3.484. Let me answer that question before I go on. When we're looking at chi-square, the actual the tables that you have will show you the number of degrees of freedom in a column, 1, 2, 3, 4. It'll show you the p-value, or the probability of being wrong if you reject the null hypothesis, like 0.10 or 0.05 or 0.01 and so on and so forth, or 0.001. Okay, now if we want to be 95% certain, or from another perspective, if we want our alpha error to be less than 0.05, right, we would choose this column here. And so if we're looking at 1 degree of freedom, the number that is the intersection of those two, 3.84, is what's going to be our critical value for chi-square. All of these numbers represent, basically what this table represents is what the critical value would be for chi-square, what value to chi-square would be if you looked at the chi-square distribution, it looks kind of like this, okay, where this is chi-square, value of chi-square going up. Okay, what that value of chi-square has to be to only happen less than 5% of the time if there's no relationship between the exposure and the illness. Okay, we don't want to, if we can make it 1% of the time, right, which means that number would have to be much larger. We can make it a tenth of 1%, a hundredth of 1%. This is asymptotic. It never really reaches this base, right? You could really go way up here. But what happens is you make it very difficult with a limited sample size to prove that there's a relationship between the exposure and the illness if you choose a very difficult threshold to reach. So typically we're satisfied with 5%. So basically, what this is telling us is that for 1 degree of freedom, 3.84 is where you have to be to have 5% left here. For 2 degrees of freedom, I don't have a table handy right now, but it might be 4.5, right? For 3 degrees of freedom, that number might be 7, and so on and so forth to get to the same point, because each one of these distributions looks a little bit different for each value, for each number of degrees of freedom for chi-square. Okay, so instead of giving you many different tables and many different graphs to look at, we give you a single table, and the only value that you really have to worry about is the one value that you really need to prove what you're looking to prove. If you need to know it more precisely, like exactly what the probability is of being wrong if you reject the null hypothesis, well, then you can use software to determine that. And software will not only give you the chi-square value, so you can make a judgment as to whether you see the critical value, but it'll also give you the precise p-value for that chi-square value. Like, for instance, if on a previous problem, this had been a chi-square value of 4.5, we know the probability is less than 0.05, right? Because we exceeded the critical chi-square value. We don't know exactly what that p-value is, right? Because it's more than our critical value, but we don't know exactly how far up this curve, this distribution it is, and what percentage is left above that. And that's what our p-value would be, our probability of being wrong if we reject the null hypothesis. Okay, so let's go back to Excel. Let me blow this up a little bit if I can. Good. Okay, and I'm going to put these numbers in here. Okay, and if I recall, I got 63 and 24. Oops, 24, and I got, let's see, 37, and that's equal to 100. And I got 76, and that's equal to 100. Right, so the total number of people involved here are 200. Oops, I'll put it in here. And let's see how many people are ill. How many people actually got ill? Some, parentheses. Whoops. Okay, equals some, parentheses. Okay, and this adds up to 200 as well. Okay, so now, let's see. This is our exposure. Okay, tuna fish, right? 8, didn't eat. Okay, and this is ill or not ill. Okay, so first thing I want to look at is what's the prevalence of illness within this group, right? Well, our prevalence is going to be equal to, let's see what our p-value is. What's our prevalence? Our prevalence for the entire population is going to be equal to 87 over 200, right? Out of this whole group, out of all 200 people, whether they ate or didn't eat the tuna salad, we had a prevalence of illness of 43.5%, 87 out of 200. That's going to come in handy in a little while, right? But in the meantime, let's calculate our various risks and odds. Okay, let's start with risk. What's the risk if you're exposed? Okay, the risk if you're exposed is going to be equal to A over A plus B. Okay, if you're exposed, risk of being of illness if you ate the tuna salad is 63 over 100. What's the risk if you're not exposed? That's going to be equal to 24 over 100. That's C over C plus D. Okay, so now what's our relative risk? Okay, our relative risk is going to be equal to the risk if you're exposed divided by the risk if you're not exposed. In other words, A over A plus B divided by C over C plus D, okay, is going to be equal to 2.625. Well, what does that tell us? that tells us that we're 2.6 times as likely to get ill, had to become ill if we ate the tuna salad versus if we didn't eat the tuna salad. Well, is that enough for me to say that there is a relationship between eating the tuna salad and becoming ill? Remember, what is our null hypothesis here? Our null hypothesis is that the tuna salad was perfectly okay. There's no that the exposure and the illness are independent. There's no relationship, right? Our alternative hypothesis is that there is a relationship. I'll give you some flexibility on how you actually phrase that, but you get the idea. That's what we're after. We want to be able to reject this null hypothesis. Okay, so now we're saying that we're 2.6 times as likely to become ill if we ate the tuna salad. That's our increased risk. Well, interestingly enough, let's say that these numbers had been reversed. Let's say that number is greater than one. Had that number been one, we would have said, well, there is no difference between whether you were exposed or you're not exposed. We would have gotten this, maybe 45 people got sick who ate it, 45 people got sick who didn't eat it. It'd be 0.45 or 0.55. That would have been one if there's no difference between the rate at which each group got ill. But it's 2.6. So now my problem now is that number big enough for me to say, it's not always going to be the same number. Is that number big enough for me to say that with 95% certainty, with less than 5% chance of being wrong, is that number large enough for me to reject my null hypothesis? In order to make that judgment, we need more than just this point value. We need a confidence interval. In other words, we say it's 2.6, but what do we really know about that number? We really need to calculate a confidence interval. If that confidence interval is 1.2 to 3.6, let's say for argument's sake, what does that tell us? We're 95% sure. We think it's 2.6 times as likely, but we're 95% sure that it's between 1.2 and 3.6, likely 2.6, but somewhere between these two numbers, we're 95% sure the true proportion lies. Okay, well, since there's no, since there the two values being independent represents a relative risk of one, what we're saying, if that's the case, is that with that confidence interval, we're 95% certain that it's not one. It's between 1.2 and 3.6, means it's also not one, right? So we can reject our null hypothesis and say that we reject our null hypothesis, we accept our alternative hypothesis. Now, had this actually been 0.9 to 3.6, well, we're not sure. We're not 95% certain that it's not one. So we can't reject our null hypothesis. We're actually going to use software later on to actually calculate that relative risk. We're not going to do that right now in Excel. Okay, so let's look at odds ratio. Okay, so what are the odds of becoming ill for each one of these groups? Well, for the exposed groups, the odds are going to be equal to 63 divided by 37, okay, or 1.7, right? It's kind of, if you look, it looks kind of almost like 2 to 1, right? In other words, there were twice as many out of 100 people, twice as many people became ill as didn't become ill. So our odds are 63 to 37, or 1.7. What about our odds if we're not exposed? Well, our odds if we're not exposed is 24 to 76, okay, which is 0.315. And our odds ratio is going to be equal to our odds for exposure divided by our odds for non-exposure, which comes out to be 5.4. A lot more dramatic looking than 2.65. But when you calculate the odds ratio for this, you'll get the same result for this in all likelihood as you would get for this. Okay, this might have a wider confidence interval than this. Again, though, the expected value for this is 1. We expect there to be no difference between the odds for people that ate tuna salad versus people that didn't eat tuna salad, right? So our expected value is 1, but the real decision making is going to be based on what the confidence interval is. That's our odds ratio. This is our relative risk. Okay, so now one other way we can approach this is to see if what our expected values for these values should be. Okay, there's our contingency table there. I'm going to create another table which is going to represent our expected values. Okay, and what are our expected values going to be? Well, we know this is 100 here and 100 here. Nothing's changed, still same number of people. Okay, our prevalence is equal to 43%, 43.5%, right? So that's the percentage of people overall that got sick during this in this population. So here's our exposed group. Here's our exposed group. Oops. Let me try this again. Here's our exposed group. Up and change something here. Okay, here's our exposed group. Here's our unexposed group. Okay, and here's our illness and no illness. I'm going to have to move that over a little bit so it doesn't think it's a calculation. And here's our no illness. Okay, so now let's take a look at what should be in this box. What percentage of this 100 people, if there's no relationship between exposed or not exposed, what percentage of this 100 people would we expect to get sick? Well, if there's no difference between exposed and unexposed, we'd expect everybody to get sick at the same rate, 43.5% of the time. So this is going to be equal to our prevalence times our p-value, our value, the number of people within that group. Okay, and this is going to be equal to just 100 minus this number. Okay, similarly, we would expect for this other group of the same percentage of people getting ill. So that's also going to be equal to 43% times 100 people. Okay, and this is going to be also equal to this number minus 100. Okay, now the thing that's unusual about this is that oops, didn't mean for that to happen. 100 minus that C13. Let's rearrange that so I get rid of that number is equal to 100 minus this number. Good. Okay, I got same numbers here in these for the exposed and the unexposed groups. The reason why that happened is because as it happened, we had the same number of people in this group as we had in this group. Had we had 80 people in this group and 120 people in this group, the numbers would have been a little bit different in these two groups, but we would still calculate the number of people that became ill for each one of these groups, exposed group or unexposed group, using the prevalence for the overall population. Okay, good. Glad to see that the audio came back there for a couple of you. Okay, so now let's take a look at this. This is our expected values. These are our observed values. So now when I want to calculate chi-square, I'm going to go through my chi-square calculation for each one of these cells, observed and expected. Say, okay, so I'm going to go through the first cell is going to be equal to our observed value minus our expected value. And I'm going to go ahead and square, let me move this over. Move it over here. Equals our observed value minus our expected value. I'm going to go ahead and square that. Okay, let me copy that. Okay, squared divided by my expected value. Okay, and that's the number I get for that. Things are looking pretty good so far, as you can see. Right now, I'm going to do the same calculation for the next two cells, this observed value and this expected value. And I can do that just by copying it down, filling it down. Okay, and similarly, I can do it for the next two cells by copying them across. Okay, you can trust me on that for now. Okay, so our chi-square value is going to be the sum of all of these values. And you can see already that our chi-square value is quite large. Our chi-square value, our chi-square value is much larger than the critical value that we need for to reject our null hypothesis. Okay, so is everybody comfortable with that calculation? Yeah. Oh, yeah. That's I changed the numbers a little bit there, didn't I? Oh, didn't I? Oh, excuse me. I didn't change them back, did I? Well, fortunately, one of the reasons why I keep telling you guys that it's really important to use Excel for a lot of stuff or learn about Excel for a lot of this stuff is because now that you know how to use Excel, you can go back and fix an error like that very simply. How is this for a good argument for using Excel? Right? I was able to go back there and didn't have to redo all these calculations, just change the cells that I had modified before. Okay, so my chi-square value is 30, which is well over my critical value of 3.84, which I would get by looking into the table in the back of Agresti or whichever table that you wind up using. Now, I just want to point out that there is a chi-square value built into chi-dist, I think it is, parentheses. There's a chi equals chi-test. Parentheses, a chi-square test built into into Excel, but it asks you first to calculate an actual range or your actual values and your expected values before you actually do the test. So our actual values is the first thing it wants, and I'm just going to highlight those 4 boxes, put in a comma, and then tell it the expected values. These are my expected values. I'm going to hit close parentheses and hit enter, and it comes up with a value 2.65 times 10 to the minus eighth, a very tiny value. Well, actually, what it's coming up with there is the p-value. It actually calculates the p-value. It's well under 0.05, right? If you really want to know what the chi-square value is, you can just use chi-inverse. Oops, chi-inverse, parentheses. Put in the probability. There's our probability, comma, and number of degrees of freedom, which is 1, right? It's just that number. That's our p-value. And it comes out to 30.94, same as we got here. See, that test takes you directly to the p-value rather than calculating the chi-square value for you. But that's available here if you want to use that. I got the expected values again. Let me just one more time. I got the expected values by figuring out what's the prevalence, what's the rate at which this entire population gets sick. Okay, and there's 200 people, right? 63 of them, 87 of them got sick. As it happened, 63 ate the tuna, 24 didn't eat the tuna, but overall, 87 people got sick. So overall, in this population, 87 out of 200 people, or 43.5% of the people, got sick. Okay, so now when I go to my expected value tables and I see that, well, there were 100 people that ate the tuna salad, well, if there's no difference whether they ate it or not, I would expect them to get sick at the same rate as the whole population gets sick, not any faster or any slower. Okay, so I notice here 63% of them got sick, more than the overall population, the combination of everybody. Okay, so you can see already that there's a difference there, right? But down here, my expected values, I want to see what those numbers would have been if there's no relationship between exposure and illness. So 43% times the number of people that were exposed is 100, is 43 and a half. 43% times the number of people who were not exposed is 43 and a half. And that leaves 56.5 for each of the each group for the people that didn't get exposed. Notice if the number of people in the exposed group and the unexposed group is the same, your expected values are going to wind up the same for those two groups because they're all based on the prevalence overall for that population. Okay, so that's how I'm going to calculate my chi-square value. All right, so now presumably we found 3 ways to demonstrate that there was a significant likelihood that if you ate the tuna salad, you were more likely to become ill than if you didn't eat the tuna salad. Okay, and we looked at that three ways. We looked at that with the relative risk, and in that case, confidence interval, the odds ratio, again, confidence interval, and with the chi-square value. Except with the chi-square value, we didn't look at odds. We didn't look at the confidence interval. We got a statistic for chi-square. We looked up on the table whether that statistic was significantly large that we could reject the null hypothesis, and as it turned out, it was. Okay, so that's how we would deal with that second one. Now that last problem on there, this last problem actually asks you to do a bit more, doesn't it? It asks you, for instance, it asks you to organize the data, asks you to report the chi-square value, asks you to report the p-value for the chi-square, asks you to calculate relative risk, asks you for the confidence interval for relative risk, right? A lot of things that involve some calculations that we weren't prepared to do in Excel. So we're going to take a look at that. Stenosis is the name of the document, and I think I have that already opened in SPSS. Let me find it. There we go. There it is. Okay. So basically, what does this file tell us? What this file tells us is that we have, let me go back to the data view for a moment. Oops. Didn't mean to do that. That won't let me. Okay. Let me get rid of that. I hit the wrong thing there. Let me pull this up a little further so I don't do that again. Okay, I have a total of 215 subjects, some of them male, some of them female, some of them, there's our gender, some of them are smokers, some of them are not smokers, and some of them that have a particular disease. In this case, coronary stenosis or a blockage in a coronary artery. Okay, so now I want to organize this data so that I can look at it from the perspective of what the risk of having stenosis is, if you're a smoker, what the risk of having stenosis is, if you're by gender, and so on and so forth. Okay, so I'm going to look at smoking and having the risk of this disease. My exposure is smoking. My outcome is disease, stenosis, yes or no. Okay, and if you look under view, if I turn off the value labels, you can see this is all actually represented by ones and twos, zeros and ones, or ones and twos. In the case of gender, it's zeros and ones. In the case of smoking, it's ones and twos. Okay, so I'm going to go back. I'll leave that turned on. Okay, so now in order to actually do this calculation, I'm going to start off by going up to Analyze. Now in Analyze, I'm not comparing means this time. I'm doing something different, aren't I? If I go into Descriptive Statistics, you'll notice that there's a category under Descriptive Statistics for crosstabs. Okay, and crosstabs means our tables. Okay, so my exposure in this case is going to be smoking. That's going to go into my rows. My columns is going to be my outcome or my disease, and that's presence of aortic stenosis. Okay, so now I have a number of options and calculations I can do now. I'm going to do these one at a time. When you're doing it, you can actually do all of these at the same time. I'm going to do one at a time just so you can see what's going to happen. First thing I'm going to do is I'm going to check off, do my observed values, do counts for observed values. I'm going to click continue, and that's the only thing I'm going to do right now. Output table comes up, and you'll notice in my output table that I have a crosstab. Smoking status, yes. Smoking status, no. Well, how many people were smokers? 94. How many of them had aortic stenosis? 51. How many people were not smokers? 121. How many had aortic stenosis? 54. A few more, but then also larger population of people within that group. What's the overall rate for this group, the prevalence in this group of aortic stenosis? Well, it's 105 out of 215 within this particular group, right? So that's our prevalence. About half of the people had aortic stenosis in this particular group. Okay, so now let's calculate what our relative risk and our odds ratios would be. Okay, first of all, risk was going to be 51 over 94 and 54 over 121. Odds are going to be 51 over 43 and 54 over 67. And relative risk and odds ratio are going to be calculated the same way. Well, fortunately, I don't have to do that. I can get SPSS to do it for me. I'm going to go back to crosstabs. It'll remember the last setting, which was already that calculates cells. Okay, this time though, I'm going to ask it to calculate also the expected values and to give me percentages by rows. I'm going to click continue, say OK, see what it gives me this time. It gives me the same box as I got before, 51, 43, so on and so 51, 43, 54, 67, except this time it actually calculates my expected values. How did it get that? Took the overall rate, multiplied it times 94 to get 45.9 people is what I would have expected to get here. And 59.1 is what I would have expected to get here. Okay, so what percentage of people who smoke have a coronary or aortic stenosis? 54.3 for the smokers and 46.6 for the non-smokers. Well, what's my relative risk? Well, my relative risk is just simply 54% over 44%, right? 54% is 51 over 94, and this is 54 over 121. So our relative risk is about, I guess, about 1.25 times as likely if you're a smoker to have aortic stenosis, maybe 1.3 or something like that. How about my odds ratio? What's that? Well, that's going to be equal to 51 over 43 divided by 54 over 67. It didn't do it in this particular situation, did it? I don't see that in this particular box. So I'm going to go back here again, analyze, descriptive statistics, crosstabs, and I'm going to go back into my cells and, excuse me, not here. I'm going to go back into statistics, and this time I'm going to ask it to calculate risk. That's my odds ratio and my relative risk. I'm going to click OK, say OK. And if I scroll down here, my box is back again. It did that calculation again. And here are my risk estimates. Okay, first I want to show you this 1.216. Okay, this table can get a little bit confusing. You'll notice that 54% over 44% is roughly 1.2, 1.2, 1.25, 1.2. You'll notice that I get 1.216 down here. Right? Well, gee, that's very interesting, isn't it? That is the result of that. Risk estimate for cohort presence of aortic stenosis equals yes. This is my relative risk right here. You could calculate it with a calculator if you're not sure. And 54.3 divided by 44.6 is going to come out to 1.216. If you don't remember which one it is, that's going to be your relative risk. 1.42472 is going to be my odds ratio. And you can calculate this again. 51 over 43 divided by 54 over 67 is going to come out to be 1.472. Okay, this is your odds ratio. This is your relative risk. Okay, so can I reject my null hypothesis and say there is a relationship in this study, based on this study, remember, that there is a relationship between smoking status and aortic stenosis? Can I reject my null hypothesis? Opinion? There's one part of this I didn't mention that is staring you in the face. What do I have here? What do I remember? That's a point estimate, right? I don't know really what the odds ratio is. I know that I estimate it to be that point, that number, right? But my confidence interval, which has now been calculated for me by ASPSS, says that the true odds ratio, 95% certainty, that we're 95% sure the true odds ratio may be 1.4, but we're 95% sure that it's between 0.85 and 2.52, which means that it could be 1. We can't say it's not 1. And similarly, for our relative risk, we think is 1.2, but we're 95% sure it's actually between 0.92 and 1.6. That could be 1 also. We haven't excluded the possibility with 95% certainty of its being 1. So we fail to reject our null hypothesis in this case. Okay, just very quickly so that guys can get ready for the next segment of this whole thing. I'm going to go back up here and I'm going to go to Analyze, Descriptive Statistics, Crosstabs. I'm going to go in here and I'm going to click on Statistics and I'm going to check off ChiSquare. and click continue. Okay, and it actually does a chi-square calculation for us as well. And here's our chi-square Pearson's chi-square, which is generally what we're using. Chi-square value is 1.962, and just as before, that's not big enough. For 1 degree of freedom, we need a chi-square value bigger than 3.84. And if you actually did the calculations, expected values and observed values, you'd find that you got 1.962, a number a little bit under 2. The probability of getting that chi-square that bigger chi-square value, if there's no relationship between the exposure and the illness, is 0.16 or 16%. It's not less than 0.05. So again, we don't reject our null hypothesis because our chi-square value isn't big enough, right? And our p-value, our significance, isn't small enough, less than 0.05. Okay, I just want to show you one more thing. Good, thank you. Failed to reject. Very good. Just want to show you one thing. I'm going to change this up a little bit, except this time what I'm going to do, analyze, descriptive statistics, crosstabs. This time, instead of using exposure smoking, I'm going to use the exposure gender. And I'm going to do exactly the same statistics. Well, let's see. Look what we got this time. This time, we got a chi-square value of 7.98. So I can reject the null hypothesis. There is a relationship between gender and the likelihood of aortic stenosis. Let me look at my odds ratio. My odds ratio is 0.462, and the 95% confidence interval is 0.26 to 0.79. It excludes one, so I can reject my null hypothesis. Same thing with my relative risk, 0.5 to 0.89. I can reject my null hypothesis. But what does this mean, this fractional value, 0.462? Before, we were talking about an exposure being more likely to cause a disease. What is the fact that this odds ratio is less than 1? What does that tell us about gender? Okay, about being female in particular, because that's the exposure. That's what we defined as exposure in this particular. What does that tell us about being female? What does being female do for your risk of aortic stenosis? Take a wild guess. Okay, I mean, you know this already. Right, it's protective, right? If this fraction is less than 1, it means the exposure is protective. Okay, guys, get ready for the next session, and I'll put this recording up as quickly as I can so that everybody has access to it, and then you guys will get to look at the recording of the other session as well. Good night. Oh, see you later, actually.